Hello, friends. Welcome to Hydraulics and Hydraulic Machines class. In today's class, we discuss on the discharge, work done, and power required to drive a reciprocating. Then let us discuss on the coefficient of discharge, slip, percentage of slip, and what is negative slip and when negative slip occurs, followed by some problems on this. Let us take straight away how to calculate or how to derive an equation for discharge. Once discharge is done, then work done equation, then power required equation. So this discussion focuses on deriving the equation for discharge, work done, power required to drive a single acting reciprocating pump. So already I mentioned it as a single acting reciprocating pump. Let us see what are the dimensions which are important for us. Let D is equal to diameter of cylinder, because this is one of the important thing, first thing. Then second is what? A. Once diameter of cylinder is known, it is pi by 4 into d square. This is what we call it as area of the cylinder, cross sectional area of the cylinder. Let R is equal to radius of crank. Radius of crank. That is also in meters. Then N is equal to the speed of the crank, because crank is the thing which is rotating. So then L is equal to length of the stroke. And then HS is equal to, it is suction head, and HD is equal to delivery head. Yesterday itself I have drawn the figure. Just for your understanding sake, quickly I will just outline the figure. So this is the cylinder and this, right? And this is the suction pipe. This is the delivery pipe. Suction valve, delivery valve. This is the sump, right? Then actually we are having piston here. And this is the piston rod. Then you can draw the crank position. This is the crank. Right? So this is the crank and this is the connecting rod, right? This is the center. This is the inner dead center, outer dead center. Here it is equal to theta is equal to 0. Here it is equal to theta is equal to 180. And if it comes back again, here theta is equal to 360. So this is, if I take it, the crank rotates like this, and this crank radius is R. Now, if you see this length of the stroke, whatever we are talking about, this length should be such that when it is at 0 degrees, it is at the extreme left, and when it is 180 degrees, it is extreme right. So that means this is nothing but the length of the stroke, which is equal to twice the radius of the crank, right? And this is of course the delivery, right? Anything you want actually. So piston, so cylinder, piston rod, connecting rod, radius of the crank, rotation, suction valve, delivery valve, suction pipe, delivery pipe. So now this crank is rotating at a speed of n rpm. This is what we mentioned. So now coming to the derivation point of view straight. What is the volume of liquid? Volume of liquid sucked during suction stroke. During suction stroke. Suction stroke, what is happening? The piston is at the extreme left and slowly the crank rotates. So the water fills up inside this, and then this entire cylinder has to be filled. What is that volume of the cylinder? So the area of the cylinder into the length. So it is pi by 4 d square into length. So this is the thing. Then if for example, now this is for one rotation, this volume of the liquid sucked during the suction stroke during one rotation, during one rotation. But how many rotations it is making actually? N rotations per minute. So if I want actually the discharge, discharge means always what actually? It is nothing but the volume per second. It is equal to area into length into how much actually, how many rotations it makes? N rotations. Per minute. But per second I want, per second, this is 60. This is the thing. A L into N by 60. Then what is the weight? The weight of liquid, deli- weight of liquid delivered per second is equal to gamma into discharge. It is equal to gamma into ALN by 60. So this is the weight actually. What is the work done actually? The work done per second is equal to weight of the liquid delivered per second into how much head actually? The total head. So it is equal to gamma ALN by 60 into HS plus HD. That's all basically, nothing else. Once again, where is the crux of it? This is very simple. But the second point, if you see, this you need to think. Why this you need to think? What I told is volume sucked actually for one suction stroke, this much actually, right? How many rotations it makes actually per minute? N. Per second, how many rotations it makes? N by 60. So for N by 6 rotations, how much is the volume? How much is the volume flowing per second? That's what I have written. The volume into basically the number of rotations per second. This N by 60 is nothing but actually the number of rotations per second. Then Once the discharge is known, then we know weight is equal to the gamma into Q, where gamma is nothing but the specific weight of liquid. If it is water, it is 9810 Newton per meter cube. Once that is over, then we know work done is equal to force, that is weight multiplied by the head, actually the distance, force into distance. So weight of the liquid delivered per second into total head. This is what we got. Then if I want, what is the power required? Power required to drive the pump. Power required to drive the pump is equal to, it is also nothing but work done per second by 1000 kilowatts. So it is equal to gamma ALN by 60 into HS plus HD divided by 1000. It is in kilowatts. That completes for us the derivation for basically in the case of a single acting reciprocating pump. What are the things? Suppose if you take a double acting reciprocating pump, double acting reciprocating pump. I don't need to do the whole derivation, actually straight away. In the case of if you want just like that, I will do the derivation also, no issues. It's a matter of 2 minutes. So let us again take the notation is same as that. Only thing is here small d is diameter of piston. Rest of the notations are as it is, whatever I have shown above, actually. If I now take it, what is the volume of water, volume of liquid delivered in one revolution of crank is equal to, how much, actually previously A into L. This is first one, right? And whereas the second thing on the other side, because on one side A into L, on the other side actually it is A dash into L. So what is A? A is equal to pi by 4 into d square, whereas A dash is equal to pi by 4 into, basically it is d square minus d square, because on the other side there will be piston rod, so that piston rod occupies all again some more area, so that's why that we have to reduce. Therefore the volume of liquid delivered in one revolution of crank is equal to pi by 4 d square plus pi by 4, pi by 4 d square into L, pi by 4 d square minus d square into L. So this is the next. Suppose now if I go for actually the discharge. Discharge is nothing but volume flow delivered per second. When I take it per second, it is L into the areas pi by 4 d square plus pi by 4 d square minus d square into n by 60. This is the next thing. Then next, actually. So this is the discharge of the pump. Suppose if the diameter of the piston, if the dia of piston is very small compared to dia of cylinder, then the area of piston can be neglected. In such a case, actually, discharge is equal to L into pi by 4 t square plus pi by 4 t square into n by 60. That means 2 times L into A into n by 60. 2 AL n by 60. This is the difference between the single acting and double acting pump. Rest is same. The work done per second is equal to automatically, so gamma q into hs plus hd. It is equal to gamma is equal to gamma q is the weight. This gamma q already just now we mentioned, it is the weight of liquid delivered per second into hs plus hd. So it is gamma into 2 ALN by 60 into hs plus hd. This completes to me the other one. And if you want the power, basically power is equal to, then naturally work done per second by 1000 kilowatts. That's it. So this completes to me the next thing. Again, short note says very, very important things. I will take it up. Then first thing is, what is coefficient of discharge? Coefficient of discharge, which you already know during fluid mechanics course. Coefficient of discharge. What is coefficient of discharge actually? Always in the case of reciprocating pump, the actual discharge QA is always less than the theoretical discharge. QA is always less than theoretical discharge. Why basically? Why? The reason being the leakages, right? Leakages actually through the valves, leakages through valves may occur, right? Then imperfect operation. Because of these things, always the actual discharge is less than the theoretical discharge. Therefore, CD is equal to actual discharge divided by theoretical discharge. It is Q actual divided by Q theoretical. This is what we call it as. Generally, this CD also in reciprocating pump, it is expressed as percentage. It actually talks about the volumetric efficiency. Volumetric efficiency. And generally how much it will be, it varies between 85% to 98%. That means that the CD value if you want it, it is 0.85 to 0.98, in that range but it is less than 1. CD is always, please remember, it is less than 1. This is the first thing. Then second thing, very, very important, I am again repeating to you all actually. What is slip? Slip is nothing but actually the difference between theoretical discharge and actual discharge. That means slip is equal to theoretical discharge QTH minus actual discharge. Very, very important. I am telling again, again, again. QTH minus Q actual. This is what we call it as slip. Generally, generally, slip is positive. Why? Because always actual discharge is less than theoretical discharge. So naturally, generally, slip is basically positive value always. And one more important thing is percentage of slip. This is often being used in centrifugal pump. Percentage of slip. Percentage of slip is equal to percentage of slip, which is nothing but actually slip Q theoretical minus Q actual divided by Q theoretical. This is what we call it as percentage of slip into, of course, 100. So it can be written as 1 minus Q actual by Q theoretical into 100. This is also can be written as 1 minus CD into 100. This we can write it as. This is the part is percentage of slip. Normally for a reciprocating pump working in good condition, reciprocating pump in good condition, percentage of slip is equal to 2% or even less. This is the second thing. Then third definition, two definitions I have completed. One is coefficient of discharge, second is slip, then third one is percentage of slip. Now next is what is negative slip. You yourself can tell what is negative slip actually. Negative slip is negative. Slip is negative means what should happen actually. Negative slip means if the actual discharge, if the actual discharge is more than the theoretical discharge. What we talked till now, we talked actually always actual discharge will be less than theoretical discharge. That is the conclusion. But there are certain conditions under which the actual discharge is more than theoretical discharge in basically reciprocating pumps actually, right? But otherwise most of the cases in reciprocating pump actual discharge is always less. But here, when this, what is this negative slip means? Negative slip occurs when actual discharge is greater than theoretical discharge. When this occurs actually, when only CD is greater than 1, then only this will occur. But when it will occur, when negative slip occurs, there are some points actually, some reasons where under these circumstances naturally the negative slip will occur. Number one, when actually, if suppose the suction pipe length is very long, the suction pipe length is long, and the delivery pipe length I mean by length means vertical length is small. That means from the sump to the pump, that vertical length of the suction pipe is long, and whereas the delivery pipe length is very small. If you see that, then understand that means if suppose this is the cylinder, for example, suppose now you have the length of the suction pipe is like this, whereas the delivery pipe is like this. If this is the case, that means this length is very high compared to this length actually. If this is short and this is more length, then actually what will happen is, and this is of course the piston. I'm not drawing the whole figure for understanding sake, right? This is the thing when it will happen. Then actually what will happen is some of the liquid without entering into the cylinder directly enters into the delivery pipe. Then if such a case, actually some of the liquid enters delivery pipe without delivery pipe directly without entering cylinder. So that means it goes straight away into the delivery pipe rather than entering into the cylinder. But your theoretical discharge is based on the theoretical discharge calculation is based on the entire liquid is entering into cylinder. What we assume when we derived the equation, what is the condition? The whole liquid enters into the cylinder. But now what I say is, without entering the cylinder, some liquid straight away enters into this. When this happens, then only, then in such a case, Q actual is greater than Q theoretical. So what are the conditions? Number one, basically suction pipe length long, delivery pipe short. Number two, what is the other thing actually? Next, pump is running at high speed. Under these two circumstances, Under these two circumstances, there is a possibility that actually some of the liquid without entering into the cylinder may directly enter into the delivery pipe. So that much liquid is not being calculated because the formula is based on the amount of liquid entering into the cylinder. So that is why actual discharge is greater than theoretical discharge. This is only under a specific special circumstances it will happen in a case where the suction pipe length is very high, delivery pipe length is very short, or where the suction head is very high and delivery head is very small. Under such cases it will happen, and at the same time the speed of the crank is so high actually. This is the case. Now let us take problems in this. Thank you.
Like, share, and subscribe. Hit the bell icon for more updates.